Hello SPH3U. This is your second video. It's the first new video, so this is new content rather than review. This one actually counts for hours. Please watch out for the quiz in EDSB after this video is posted. So today's topics are number one, the physics definition of power. So what does power actually mean in the physics sense? We're going to do some basic practice problems in power and efficiency. We're going to talk about measuring large amounts of energy in kilowatt hours. So you might imagine that watts are going to be part of our lesson today. And we're going to talk about Ontario's electricity generation. So we're going to have a look at the different energy sources that we have here to make electricity for us. Let's jump right into it with our current topic, the physics definition of power. And we're going to start with a question for you. If I could take away my learning goals, there we go. Start it with a question for you. We have 4 items here. Actually, I'm going to put my thing in the left-hand side here. We have 4 items. We have a tractor, we have a rock climber, we have a AK-47, and we have a Toyota Camry. So this tractor is the #1 most operated tractor in the world apparently right now. This is the #1 best-selling car in the world. This is just some random rock climber's picture, and this is the #1, assault rifle in the world. So the question is, which one of these has more power? And it's a bit of a thinker, because you guys might have a different definition of power than someone else does. What are we measuring in terms of power? Is it the power to plow a field? Because this thing's going to do way better than any of these at plowing a field. It's going to be kind of silly to plow a field with an AK-47, right? Or is it climbing up a wall? Because, I don't think this thing could climb up a rock wall, and neither could this. And that would look pretty funny doing it. Or is it going between 2 cities? Because then you'd rather have the car than the tractor. So power is an interesting concept. But we do have a unit of power, right? We have a unit of power that a lot of people know, and that unit is called horsepower. So which one do you think has more, let's actually change this, more horsepower, right? And what is horsepower? Let's think about it for a second. 5, 4, 3, 2, 1. And you're probably stuck between the tractor and the car, because pretty sure the person has less horsepower than either of these. And I don't even know how you would calculate the horsepower of a gun. We'll give it a go later, actually, in this video. So you're stuck between the tractor and the car. So which one do you think had more power? Which one's more powerful? Well, it might surprise you to learn that it's actually the car. It's the car, and it's the car by a factor of 2. This tractor has about 92 horsepower. This car has about 180. So this car is twice as powerful as this tractor. But wouldn't you want power in a tractor more than you want power in a car? Well, here's the thing. Cars have to be fast. Tractors don't have to be fast. So this is the thing about the physics definition of power. Power is, it's gonna be up in the keep in mind. It's the speed of energy transfer. It's the speed of energy transfer. The speed of energy transfer. So it depends on how fast something can transfer energy into something else, or gain energy from something else. So if it's a speed, right, and speed is something over time, right? Always something over time. Let me move my thing out of the way. There we go. All right, speed is always something over time. You can have, the speed of, normal speed is distance over time. But in this case, power is energy over time, and not actually energy, it's the change in energy, right? Energy transfer over time. Energy transfer over time. That's the thing that we're we're looking at. So this might help you understand why the car actually needs twice the amount of horsepower as the tractor. The car needs to accelerate pretty quickly. It gets a lot of kinetic energy very quickly, whereas the tractor doesn't really need to gain a lot of energy particularly quickly. It just needs to, slowly move through a field. Traction and friction and stuff is far more important for this thing, so it's got these big tires. But yeah. And of course, the human's in a completely different league, but we'll talk about that. And the gun, yeah, interesting. So, power is energy transfer over time, and it might be easier to talk about what we use as energy transfer, which is work, right? Work is just our definition of energy transfer, and it's work over time. So, if you want a formula for it, it's actually in your formula sheet here, but I've done a thing where I can actually pull up the formula sheet on screen. I should have done a thing where I can pull up the formula sheet on screen. Apparently I didn't. Oh, there we go. And I can now actually show you that energy, that formula. Here it is. Right? There's the formula here. Power is change in energy over change in time, which syncs up nicely with this formula, which is work is the change in energy. Right? So change in energy over time, over elapsed time, that's power, and that can stay down there for a while. So yeah, so the speed of energy transfer, that is the definition of power. Power, the SI unit of power, is watts, named after this guy, James Watt, dead white guy, the usual thing. Now the SI unit has to be in kilograms, meters, and seconds, right? Remember, SI is kilograms, meters, and seconds. Kilograms, meters, and seconds. So, therefore, 1 watt is actually 1 joule per 1 second, right? It's 1 joule per second. So watts are measured in joules per second. If you ever wondered what the wattage on like a light bulb or whatever is, it's in joules per second. Now the question up here was which has more horsepower, and horsepower is also a measure of power, and that's down here, 1 horsepower, and it is 745.7 watts. There's the specific definition of horsepower. Most people go with 746 watts, right? So if you want to just remember 746 watts, you can do that. Yeah, so that's how much energy a horse can put out over a long period of time. That's how horsepower is measured. So there's this physics definition of power. All right, now that we have this equation that we can play with, right? This equation down here that we can play with, we can do some practice problems with it. So I'm going to pause the video for a second and get over to some practice problems that involve power. And we're back. So I've got the worksheet back here with some power problems on it. Just to review our learning goals, we've done the physics definition of power, which is the speed of energy transfer. We have our formula sheet here, which annoyingly, oh, I see what's happening. The formula sheet here, which is power is energy over time. How do we get over there? That's kind of annoying. That's weird. My thing's not working the way it should be. Well, I'm going to pause and fix that. Give me a sec. Okay, I fixed it. So now the formula is going to stay in the bottom of the screen all the time, and I've got this in the background. So we're going to do some power and efficiency problems. On here, and I've changed our current topic to some power and efficiency problems. So take that away, and let's have a look at our first problem, which says a student lifts a bucket with a 98 Newton force in 30 seconds out of a well. The bucket is lifted 30 meters. So let's jump over to this view. Oh, gotta pause that again and fix that again. Sorry, just a sec. Okay, hopefully that's fixed for good. Let's actually do this problem here, move that out of the way. So we have our formula down here, power is energy over time, and we have our setup here, our information. So let's see what's going on here with this bucket. We have a bucket, it starts down here, it moves up to here. We know its mass. Well, we don't know its mass, we know the force. The force is 98 newtons. We also know the distance is 30 meters. And we know that the time was 30 seconds. That's what's given to us in our formula, in our question. We're first asked how much work is done on the bucket by the student. Well, this isn't the equation for work, so we got to go hunting in our equation sheet. Let me find that. Here's our two equations for work in our equation sheet. Which is work is force times distance, or work is the change in energy. Well, we don't know the change in energy. We could figure it out because we know the force and the distance. So we're going to use this equation, work. So A, right? Work is force times distance, which means it is going to be our force, 98 newtons, times our distance, which is 30 meters. We're going to get an answer, which I need the calculator for. So let's pull up the calculator. Calculator. The calculator is going to, we're going to clear that. So 30 times 98 equals 2,940. 2,940. What's the unit? Well, it's going to be 2,940 joules. So take away the calculator. Right? It's 2,940 joules because of work, right? It's an energy term. Or Newton meters if you prefer. Newton meters. So that's the amount of work done here. Of course, sig digs say it's going to be 3,000 joules because we only have one significant digit in our 30 meters here. So only one significant digit. We can only trust this to 1, so 3,000 joules. Now part B of this question, I'll pull away the calculator. Part B of this question is how much power is exerted by the student. So using, now we can go over to our power formula, which is that one. Right, and we can figure out how much power is exerted by this student. Power, right, part B, power is the change in energy over the change in time, or equivalently, it's work over time, work over the change in time. And we just figured out the work, and we know the time, we get 30 seconds. So this is 2,940 joules over 30 seconds, which will actually just, because that was 30 and that's 30, it'll actually just bring us right back to 98. Not newtons. Oops, sorry, not newtons. We have a new unit for this, right? Work is measured in work. Work is joules. Time is seconds, and joules per second is equivalent to a watt. A watt. Some people put the little things on there just to make it look fancy. So there we go. There's an answer, but of course sig digs, because it's one sig dig there. It's about 100 watts. 100 watts. So now you know what a watt is. Let's try another practice problem just to make sure that we've got it. And I'll just pull up on you. I know I'm going to erase it. So please make sure that you understand how we solved this problem for getting the work, and then using that work that we calculated. Right, that's the work we calculated, and work over time, the speed of energy transfer, gave us the number of watts. So moving on. Let's try something else. This one's kind of annoying. Try it if you want, but yeah, that's not a good one. This one's interesting because it's talking about efficiency and power and work. So maybe we'll try this one out because this puts everything together. A 500 watt electric motor lifts a 20 kilogram object from 5 meters in 3.5 seconds. So this one almost kind of is a backwards thing. We can think about it backwards. So we have a motor and it's 500 watts. Right, and let's think about what a watt means. A watt is 500 joules per second. Every second that this thing is on, it's 500 joules of energy that it can make. Right, and it's, you know, connected to some kind of pulley, right? Some kind of pulley up here, and it's lifting an object that weighs 20 kilos, and it's lifting it a distance of 5 meters. Okay. So we've got a distance. Delta D is 5 meters. We know that work is force times distance, so that's good. If we have a distance, we can figure out the work if we just had a force. We also know the time. The time is 3.5 seconds. So delta T, 3.5 seconds. Right? Delta T is 3.5 seconds. So let's solve it. Right? We would, in order to figure out the work done. Well, we know the work that was put in by the motor, because if power is energy over time, right? If power is work over time, we could actually just figure out energy, right? Figure out energy or work, which is what we're interested in, because you know that and that are exactly the same quantity. Work is the change in energy. So if we want to figure out work, we just multiply by delta T on both sides. Right, this one will reduce to 1, so work is power times time. Power times time. So we've got power times time and force times distance. So this one we already know. We have 500 watts, and we know it was on for 3.5 seconds. So 3.5 seconds. Right, that's delta time. That's power, which means we get 3.5 times 500. 1500 plus 250, so 1750 joules of energy. 750 joules of work in, work that went in, energy in. So this motor has used 1750 joules of energy. Let's see how much energy it got out. To do that, we need to figure out the force on this object, and the force that it's working against is going to be gravity, right? So in this case, then that's Fg. And Fg, we have an expression for it. It's m times g, and that's found in your, it's found here. mgh, Eg is mgh. That's right there. So you could just use, this guy. Eg is mgh for the change in gravitational energy. That could be your delta E. That could be your work. And it's, or here we can use delta D times delta D. It gives you the same thing, right? Mg delta D. Here delta E D is the h. It's the height that it's moving through, because that's in line with the force of the motor, which is trying to cancel out the force of gravity. So mgh, we got 20 kilos times 9.81 newtons per kilo times delta D, which is 5 meters. Man, that's going to mess up my sig digs, right? That's only one significant digit. That's not going to be great. So let's solve it. This times this is 100 times 9.81 is going to be 981 joules, because this is a work. This is kilogram Newton meter. There's a Newton meter, right? The kilograms are going to cancel. You get newtons times meters, which is joules. So that's the work out. That's how much work came out. Right? To remind you what the question was, what is the efficiency of the motor? And the efficiency is going to be what we got out of the motor divided by what we came in. So what we put in. So percent efficiency is, in this case, work out over work in, which is 981 joules over 1,750 joules, right? This is how much energy the motor used, maybe it's electrical energy from the wall or something, and this is how much useful energy we got out by lifting this thing. Everything else must have gone to friction and heat and noise and vibration and all that kind of stuff, which I can't do that in my head. That's J for joules, not a 5. Oh, that still looks like a 5. Let me fix that. 951 joules. There we go. That looks better. 951 joules. There we go. Let's pull up the old calculator and calculate that. So calculator. Let's have a look. It's 981 divide by 1750, 0.56. 0.56 is what I get. So take away the calculator, and 0.56, so times 100%. So that's 0.56 times 100. So it's 56% efficient. But of course we only have one sig dig because of this 5 over here. It's one significant digit because whoever wrote this worksheet didn't think about that. So we actually have to write 60%, approximately 60% efficient. So there's some power and efficiency practice problems. There's some other ones that I could ask you to do, but I'll just attach this worksheet to the EDSB post. Like for example, there's there's this one. This might be a good one to try, where you get the power and the efficiency, so that means that you can use that to figure out the useful energy that we get out. So it's like reversing this process, and then reversing this process to figure out the time, how long it will take. So there's some practice problems. I'm going to pause the video for a second. Okay, and we're back. So next section here is a useful shortcut for power, some useful shortcuts, and that's to realize that you can combine these things if you're using meters, seconds, and kilograms to great effect. Here, for example, a 100 watt electric motor, this is the problem that I was talking about earlier, has an efficiency of 82%. How long will it take to lift a 50 kilogram object to a height of 8 meters? If we think about this one, if it's 100 watts, right, 100 watts, you can start combining your concepts to great effect here. So 100 watts is 100 joules of energy in per second, right? 82% efficiency means that that 82 watts out of those 100 watts will be useful, right? Will be useful. So you can actually use efficiency straight out of power instead of using energy. The reason we can do that is, like, think about it in 1 second, right? Every second, right? 82 joules out of every 100 joules every second are going to be useful. Then we got this 50 kilogram object, and it's lifting it to a height of 8 meters. So you're going with, you've got 82 joules a second, joules per second of energy going in, and the energy, the gravitational energy of this object, a 50 kilogram object at a height of 8 meters, is going to be m times g times h. So we could work that out, right? Its mass is 50 kilos, the gravity 9.81 newtons per kilo, and the height here is 8 meters. Right, let's solve that with a calculator. Calculator, turn that up. 50 times 9.81 times 50 times 9.81 times, so 50 times 9.81 times 3924. So 3924. 3924. And what's our unit? Well, the kilograms will reduce the kilograms, Newton times meters. Newton times meters is just a joule. Right. So you've got 3924 joules, and every second this motor can pull out 84 joules. Let me just take away the calculator there. You've got this many joules of energy to put into the object, and every second 82 joules per second, right? At 82 joules per second. So it really is like a speed. You can consider this like a speed. Easy enough. If power is energy over time, as mentioned down in the corner here, right down here, power is energy over time. Then time, you know what, I'm going to jump over the whiteboard for this because the rearrange is going to look weird on here. So jump over the whiteboard for a sec, and in a different color I'm going to rearrange that real quick. So power is energy over time, and we want time, right? We want to arrange for time. This is one of those kind of tricky rearranges. What you have to do is you have to multiply by time on both sides. Time on both sides. This will reduce to 1. That'll stick around. So delta T times P equals delta E. And then you divide by the power. So divide by power. Now the power will cancel out on this side. We'll reduce to 1 on this side. And so delta T becomes delta E over P. Right? Delta T equals delta E over P. There's kind of an interesting shortcut to that, where the original equation was power is energy over time, and what we kind of did was swap these two. Right? We just kind of swapped those two. Be careful with that, because it only works if it's a single term on this side. If there's anything that's added or taken away, you can't do the swap. The swap doesn't work. So yeah, so time is energy over power. Time is energy over power. Change in energy over power. Just like time is distance over speed, if you want to think about it that way. This is the distance we have to go. This is how many joules we have to transfer. This is how fast we're transferring the joules. So back to this view. There I am in the corner. We just learned that time is energy over power. Right. And so that is 3,924 joules divided by 82 joules per second, 82 watts, which is some number that I need the calculator for. So I'm just going to divide by 82, 47.85. That's 47.85. 47.85. Can't type. 47.85 seconds, because it's a time. That's how many seconds. We do have to check our sig digs. We only get one sig dig, so this is 50 seconds, and that seems reasonable for lifting up a heavy object using a 100-watt motor, right? It seems like it would take a while. So that's that. Right, but I promised you an interesting shortcut. So the interesting shortcut here is, if work is, I'm going to arrange this one on the, I'm going to make a new page here. I'm going to arrange it on here. All right, we'll do another little rearrange magic over here. Right, we know that work is force times distance. And we know that power is work over time. So if we put that together, right, if we take this work and just stick it in right there, that means power is force times distance over time, right? Or, because commutative property of multiplication, force times distance over time. Force times distance over time. Or it's force times speed. This is really useful if you have something traveling at a constant speed. You don't need to solve for, if you have the speed, and if it's maybe it's working against friction or something, you don't have to solve for the energy if you have the force. So that's kind of a useful shortcut that you can keep in mind, that power is force times speed. So yeah, it's kind of a cool formula. I don't put it on the cheat sheet because you can solve it just from basic principles, but I like it. Power times speed. Okay, back to this view. Let's, we'll take that away. There's a brief thing about efficiency here, right? Watts and lumens and stuff like that. And the upshot here is efficiency can be energy out over energy in, but it can also be power out over power in. So it doesn't have to be just energy. You can just use the watts. You don't have to use the joules. Watts works just the same because you just kind of assume that it goes for 1 second, and that's good. So that's that piece. I think that takes us to the next topic. So I'm gonna get ready for the next topic. You know what? I'm gonna solve this question after the video. This will be an optional thing at the end of the video that I'll solve. If you guys want to check out how efficient this conversion is, it'll be at the end. Okay, so let's talk about energy generation, which means that we have to change, we're into energy generation now. So I'm going to change this down here to energy generation. Current topic, energy generation. And keep in mind, of electricity all the time. Right, and we got to keep in mind the supply and demand of electricity is going to change all the time. So let's jump over to this really cool website that I wanted to show you guys, which is this. There will be a link to this website. Down in the description, but it's live power data. Right, it's live power data, and you can see the demand of electricity and the market demand in megawatts. Remember, a watt is a joule per second. A megawatt is 1,000,000 joules per second, and you can see what everything is outputting right now, stuff like that. And even better than that, they have live curves. So right now we're coming into peak demand, right? So we're seeing the demand of electricity over time. This is 6, 7, 8 o'clock, 7 and 8 o'clock. Why do you think demand for electricity spikes at 7 or 8 o'clock? Take a minute to think about it, and you might realize that it's probably because people are cooking dinner, maybe, or they're turning on their TVs to watch a show or something like that. You can see a similar spike around noon. So maybe that's them cooking lunch, putting on the kettle to make some tea or whatever. And there's a little spike just as people wake up in the morning, so they're taking their showers and whatever. So yeah, it's interesting to see the demand curve And we can actually see that the demand during weekdays, this is weekdays here, is higher than the demand during weekends. Because during weekdays there's people working. So yeah, that's energy generation. Our energy supply has to match that demand. So you can see kind of how well they're trying to match that curve. Here's the demand curve. Here's our electricity supply. You can see that it kind of follows the same sweep. And this thing's actually broken down by type. This big orange thing, this just constantly going at like 10,000 megawatts for the whole day and night, is the nuclear baseline. That's all our nuclear plants that makes most of our energy. Right? You can see that it just goes just constant. The light blue is hydro, so it changes. They can ramp it up and down to meet demand. You can see, for example, that they tend to ramp it down a little bit in the afternoon on weekends. The green is wind energy, and of course it's just going to depend on whether the day is windy or not. So you can see certain days they were windier and certain days they were less windy. So if you remember, we had a lot of wind about 2 days ago. That actually gave us a lot of wind energy. So that's pretty cool. And there's some other ones. You can actually see the yellow is solar. So during, here at noon, here at noon, and here at noon, here at noon, and here at noon, and here at noon, you see the solar. And you can actually kind of tell when there were sunny days and when there were cloudy days, because there was more solar on the sunny days. So this was a cloudy day, and this was a sunny day. All right. So that's our energy generation here in Ontario. I've got a kind of a breakdown here from 2017, but I just really like this graph. You can see that most of it's nuclear, a lot of it is hydro. We have some natural gas plants. Those are used to quickly meet demand if demand is outstretching supply. Right? You can see, for example, I can take away. I should be able to take away gas or nuclear. No, I can't. That's unfortunate. I wish I could have zoomed in just to the gas and taken away all the other ones, because it would be fun to just look at just the gas plants ramping up and down production to meet demand. That would be really neat. And then we got biofuel, which is right now very, very small, but growing bigger, which is pretty good. Okay, so that's electricity generation. Now notice we need to make a lot of electricity in the megawatts, millions of joules per second. Every single second we have to make millions of joules. So the next topic here is measuring large amounts of electricity, of energy in kilowatt hours. You might have heard of kilowatt hours. If you have a power bill around your house, go find it, and it'll have stuff in kilowatt hours, because that's the current pricing model. So let's talk about kilowatt hours, and I'm going to change this over to kilowatt hours. Kilowatt hours. The joule is a very small unit of energy. Right? So keep in mind that the joule is a very small unit of energy, so we need a better way to measure this thing. That's the kilowatt hour. So that's what we're going to talk about here. We're building a kilowatt hour. So let's talk about a question. Question here. You might see here like different costs of electricity per kilowatt hour. Here's a question. My fish tank heater has a power of 75 watts. If it's on for 15 minutes, how much energy did it use? So, maybe take a minute to answer the question. And we're just going to answer it here. 75 watts. Watts means 75 joules per second. Right? And 15 minutes times 60 is a lot of seconds that I don't have time to do in my head right now, so I'm just going to do it on the calculator here. 15 times 60, 900. It's 900 seconds. 900 seconds. So just the heater in my fish tank, right? Just the heater in my fish tank in 15 minutes is going to use 75 times 900. 75 times 900. 75 times 900. 75 watts times 900 seconds equals 67,500 joules, which is a lot, right? And you don't want to have an amount on your electricity bill in like billions of joules. So it's easier to talk about it in terms of kilowatt hours or watt hours. Right? So 15 minutes. Let's do this in watt hours. In watt hours, this changes to 75 watts for 1/4 of an hour, right? And that's equal to what we might call 75 for is, unless my math is wrong, is 18.75 watt hours, right? That's watt hours, or 18.75 watt hours. That's what watt hours, that's the unit. Now a kilowatt hour is 1,000 of those. So it's so if we think about kilowatt hours, 0.01875 kilowatt hours. And that's the unit. The unit is a small k, big W, little h. Small k for kilo, big W for watt, small h for hours. Here we see the costs. So, you know, even on peak, my fish tank is like a fraction of a cent per hour. Yeah. So kilowatt hour, it's 1 kilowatt for 1 hour of time. So that's 1,000 joules per second for 1 hour. All right, 1,000 joules per second for 1 hour. And there are 3,600 seconds in 1 hour. 3,600 seconds in 1 hour. So therefore, 1 kilowatt hour is 1,000 joules per second. 1,000 joules per second times 3,600 seconds, which is equal to 3.6 million joules, right? 3.6 million joules. And that is an exact number, right? Because it's 1,000 and 3,600, those are counts. So that's an exact number. 3.6 million joules in 1 kilowatt hour. So now you can solve problems involving kilowatt hours, and I'll have some practice problems like that up with this note. So that's the end of the lesson, right? We've talked about the physics definition of power in terms of energy over time. We've done some power and efficiency problems over on the board, right? We solved a few together, you know, those kinds of questions. We talked about Ontario's electricity generation and how it has to match demand and supply, and some of the different things we have, like that nuclear baseline. And we've talked about measuring large amounts of energy in kilowatt hours. So 1 kilowatt hour is 3.6 million joules. Exactly. It's exactly 3.6 million joules. And that's the end of the lesson for today. Thank you very much, and keep an eye out for the quiz. Thanks.